The universe is ruled by forces beyond our everyday comprehension. From the tiny bonds holding atoms together to the colossal energies shaping entire galaxies, these powers define reality itself. This is a countdown of the 30 most powerful forces in the cosmos. By the end, you will understand the fundamental engines driving everything that exists. We will explore why empty space is not empty and what could tear a star apart. What single cosmic force do you find the most fascinating? Our journey begins not with a bang, but with a whisper from the void. Vacuum energy, often called dark energy, is the mysterious force causing our universe to expand at an ever-increasing rate. Think of the fabric of space itself not as an empty stage, but as a restless ocean. Even in its calmest, most empty state, this ocean seethes with a hidden energy, a constant pressure pushing galaxies apart. It is the dominant force in our cosmos today, a ghostly presence more powerful than gravity on the largest scales, yet its true nature remains one of physics' greatest mysteries. But to understand the very large, we must first look at the impossibly small. Inside every atom, a titan holds the core of reality together. This is the strong nuclear force, the mightiest glue in the universe. It acts like an unstoppable binding energy between quarks, the fundamental building blocks that form protons and neutrons. Without this force, the positively charged protons in an atomic nucleus would violently repel each other due to their identical electric charges. The strong force overpowers that electromagnetic repulsion, locking the nucleus together and making matter possible. It is the ultimate cosmic cement, operating over a minuscule range but with an almost unimaginable strength. Bridging the world of the atom and our own is a force you experience every single second. Electromagnetism is the artist of the visible universe. It is the force behind every beam of light, every color you see, and every chemical bond that builds molecules. It holds your very atoms together and allows your nerves to communicate. While the strong force is confined to the atomic nucleus, electromagnetism's influence extends infinitely, governing everything from the structure of a DNA molecule to the fury of a lightning storm. Together, these three forces paint a picture of cosmic power, from the silent expansion of the vacuum to the fierce bonds in the atom and the brilliant energy that illuminates our world. Yet for all its power, the strong nuclear force is not the only ruler within the atomic nucleus. A far more subtle and transformative power also operates there, one that can literally change one type of matter into another. This is the weak nuclear force, the master of radioactive decay. It is the force responsible for a process called beta decay, where a neutron spontaneously transforms into a proton, ejecting an electron and a ghostly particle called a neutrino. Without this transformative power, the sun would not shine. The weak force is the crucial first step in the chain reaction of nuclear fusion, allowing protons to fuse and ignite the stellar engines that light the cosmos. It is a quiet, subatomic alchemist, reshaping the very elements of existence. While the weak force works on the smallest scales, its cosmic cousin creates ripples felt across the entire universe. Gravitational waves are not a force in the traditional sense, but the very echo of force in motion. Einstein predicted that massive, accelerating objects, like orbiting black holes or collapsing stars, would send waves through the fabric of spacetime itself. These are not waves in space, but waves of space, a stretching and squeezing of reality as they pass through. For a century, they were just a theory. Then, in 2015, we first felt these cosmic tremors, detecting the faint whisper from a collision of two black holes over 1 billion light-years away. It was the sound of spacetime ringing. From the silent ripple of gravity, we turn to a force you can literally feel on your skin on a sunny day. Radiation pressure is the gentle but persistent push of light itself. Every photon, every particle of light, carries a tiny amount of momentum, and when it bounces off or is absorbed by a surface, it gives it a small push. In the vacuum of space, this pressure from starlight can push vast clouds of cosmic dust into intricate shapes. It is the principle behind the dream of light sails, where spacecraft could one day cruise the solar system propelled by nothing but the sunlight, catching the photon wind like a yacht on a cosmic ocean. These three forces reveal a universe of constant change, from the transformative decay within atoms to the rippling of space-time and the gentle, persistent push of starlight. That gentle push of starlight is a whisper compared to the brutal, stretching pull near the most massive objects in existence. Tidal forces are a gravitational extreme, a difference in the strength of gravity between one point and another. If you were to fall feet first towards a black hole, the pull on your feet would be so much stronger than the pull on your head that your entire body would be stretched into a long, thin strand of atoms. Scientists call this spaghettification, a fittingly dramatic name for a force that can tear entire stars apart. These forces are not just destructive, they also create order, like the tidal locking that keeps one face of our moon permanently turned toward Earth. From this violent gravitational gradient, we find a force that creates invisible structures across the cosmos. Magnetic fields are the great organizers of chaos. Born from the motion of charged particles, these invisible lines of force can sculpt vast clouds of interstellar gas into breathtaking nebulae, channeling superheated plasma into jets that stretch for light years. Closer to home, our own planet's magnetic field acts as a protective shield, deflecting the sun's deadly radiation and making life on Earth possible. This force turns random motion into magnificent architecture. But what set the stage for all of this structure in the first place? To answer that, we must look back to the very beginning, to a fraction of a second after the universe was born. Cosmic inflation is the theory that our entire observable universe underwent a period of unimaginably rapid, exponential expansion, growing from smaller than a proton to a vast volume in less than a blink of an eye. This incredible burst did not just make the universe big, it made it uniform, planting the tiny seeds of density that would, over billions of years, gravitationally collapse into the galaxies and cosmic web we see today. It was the ultimate opening act, setting in motion everything that would follow. That explosive birth of cosmic structure was just the beginning, for another invisible architect was already at work, sculpting the universe in secret. Dark matter's gravitational influence is the hidden hand guiding the cosmos. We cannot see it, touch it, or detect it with any telescope, yet we know it is there because of its powerful grip on everything we can see. Its gravity dictates how fast galaxies spin, preventing stars from being flung into the void. On the largest scales, it forms a vast, invisible scaffolding, a cosmic web upon which galaxies are strung like glittering dew on a spider's web. Without this dark gravitational glue, our universe would look nothing like it does today. But where dark matter builds, another force delivers the elements for life. A supernova shockwave is one of the most violent events since the Big Bang itself. When a massive star exhausts its fuel, its core collapses in a heartbeat, rebounding in a cataclysmic explosion that outshines an entire galaxy. The resulting shockwave blasts outward at millions of kilometers per hour, forging heavy elements like gold, silver, and uranium in its fiery heart, and then scattering them across interstellar space. These stellar tsunamis can also slam into nearby gas clouds, compressing them so violently that they collapse, triggering the birth of new generations of stars. We are all, quite literally, made of stardust forged in these blasts. The aftermath of such stellar fury does not simply fade away. It can create gales powerful enough to shape the destiny of an entire galaxy. Galactic winds are colossal outflows of superheated gas, driven by the combined fury of exploding stars and the intense radiation from supermassive black holes at a galaxy's core. These winds can rage for tens of thousands of light years, carrying the very raw material for future stars out into intergalactic space. This self-regulates a galaxy's growth, effectively turning off its own star-forming factories and preventing it from becoming too large. It is a dramatic feedback loop, where the ferocious energy of creation itself can ultimately halt further creation, a cosmic balance between life and death on an unimaginable scale. These galactic winds are born from chaos, but some cosmic forces represent a perfect and final order. A black hole's gravitational pull is the ultimate expression of gravity's power, a point of no return so absolute that not even light can escape its clutches. The boundary of this prison is the event horizon, a spherical shell marking the edge of our observable universe. Cross it, and every possible path leads inward to the singularity, a point of infinite density where the known laws of physics break down entirely. Yet outside this point of darkness, there is often a blaze of light. Matter spiraling into the black hole forms a superheated accretion disk, a whirlpool of plasma so energetic it glows with the light of billions of stars, a final, brilliant scream before being swallowed by the dark. From this absolute dominion of gravity, we shift to the smallest possible scale, where the very concept of nothing ceases to exist. Quantum fluctuations are tiny, temporary changes in energy that occur even in a perfect vacuum. According to quantum mechanics, empty space is not truly empty, but a seething sea of virtual particles that constantly pop into and out of existence, borrowing energy from the void for a fleeting moment before annihilating each other. This isn't just a theoretical curiosity, it might be the very origin of everything. Some theories suggest our entire universe was born from a massive quantum fluctuation in a primordial nothingness, a single, unimaginable spark that ignited the Big Bang. And what gives substance to the particles born from this quantum foam? An invisible field that fills all of space. The Higgs field is like a cosmic molasses that permeates the entire universe. As fundamental particles move through this field, they interact with it, and this interaction is what we perceive as mass. Think of a famous person trying to walk through a crowded room. They move slowly because they are constantly stopped for autographs and handshakes. A particle with a strong interaction with the Higgs field, like a top quark, has high mass and moves sluggishly. A particle like a photon, which does not interact with the Higgs field at all, is massless and zips through the cosmos at the speed of light. This mechanism gives the fundamental building blocks of matter their substance, transforming ethereal energy into the solid stuff of reality. While the Higgs field gives mass to the particles of the universe, some objects wield magnetic power so extreme it defies comprehension. Deep in space, the collapsed cores of dead stars known as magnetars possess magnetic fields that are truly monstrous. These fields are trillions of times more powerful than Earth's protective magnetic shield. If a magnetar were located as far away as the Moon, its magnetic pull would be strong enough to erase the data from every credit card on our planet. The energy stored in these fields is so immense that it can crack the star's own solid crust, causing catastrophic starquakes that release titanic bursts of gamma rays, flashing across the galaxy like cosmic lighthouses of pure force. These magnetic titans can accelerate matter to incredible speeds, and they are not the only source of such ultra-fast particles. Cosmic rays are atomic fragments, protons and atomic nuclei, that travel through space at nearly the speed of light. They are the universe's natural particle accelerators, far more powerful than anything we can build on Earth. Their origins are diverse, born in the shockwaves of supernova explosions, unleashed from the violent environments around black holes, or perhaps blasted from the magnetospheres of spinning pulsars. When these high-energy projectiles strike our atmosphere, they create cascading showers of secondary particles, a constant, invisible rain from the cosmos that subtly contributes to the natural background radiation we experience on Earth. Unlike these distant cosmic bullets, there is a stream of charged particles that constantly flows from our own local star. The solar wind is a continuous, supersonic outflow of plasma, primarily electrons and protons, blowing outward from the sun's superheated corona. This wind may be far less energetic than cosmic rays, but its effects are direct and visible. When these charged particles are captured by Earth's magnetic field, they are funneled toward the poles, where they collide with atoms in our atmosphere, energizing them and causing the breathtaking, shimmering curtains of light we know as the aurora. But this wind also shapes the space around all the planets, carving out protective magnetic bubbles called magnetospheres, and over billions of years, it can even strip away the atmosphere of a world that lacks a strong magnetic shield of its own. The solar wind is a gentle breeze compared to the hurricane of a galactic collision. When two entire galaxies are pulled together by their mutual gravity, they engage in a slow-motion dance spanning billions of years. Stars, separated by vast distances, rarely crash, but the immense clouds of gas and dust slam together violently. This cosmic car crash compresses the gas, triggering ferocious waves of new star formation, called starbursts, that light up the galactic structure in brilliant blue. The galaxies' shapes are utterly torn asunder, their spiral arms stretched into long, streaming tails of stars by immense tidal forces. We are witnessing the future of our own Milky Way, which is on a collision course with the Andromeda Galaxy. This monumental merger will fundamentally reshape our night sky, eventually creating a single, giant elliptical galaxy. But from these slow, majestic collisions, we turn to the most sudden and violent explosions in the universe. A gamma-ray burst is a cosmic flashbulb, a beacon of pure energy. For a few seconds, this single event can outshine every star in 100 billion galaxies combined, releasing more energy than our Sun will over its entire 10 billion-year lifetime. These bursts are thought to be the birth cries of black holes, unleashed during the collapse of the most massive stars or the mergers of ultra-dense objects like neutron stars. They are the universe's ultimate reset buttons, and if one were to occur too close to Earth, its radiation could sterilize the planet. Yet, even these titanic blasts can be warped and magnified by an invisible cosmic phenomenon. Gravity can bend the very path of light itself. Gravitational lensing occurs when the immense mass of a galaxy cluster curves the spacetime around it, acting like a giant lens in space. Light from a more distant galaxy traveling toward us follows this curved path, resulting in distorted, magnified, and often multiple images of the same background object. This is not an optical illusion, it is a direct prediction of Einstein's theory of general relativity. These natural telescopes allow us to see galaxies that would otherwise be far too faint and distant to observe. Crucially, by studying how the light is bent, astronomers can map the distribution of all the mass in the foreground cluster, including the vast, invisible halos of dark matter that dominate its gravitational pull. While gravitational lenses warp the fabric of space to show us distant light, a far stranger connection operates instantly across the cosmos. Quantum entanglement is a phenomenon so bizarre that Einstein himself called it spooky action at a distance. It describes a pair of particles like two electrons that are created or interact in such a way that their properties become permanently linked. They form a single, unified quantum system. If you then separate them by any distance, even across the galaxy, measuring one particle will instantly determine the state of its partner. It is as if flipping a coin in your hand immediately forces a coin on the other side of the universe to land on the same side. This is not a signal traveling faster than light. It is a deeper connection that suggests the universe is fundamentally non-local, that separateness may be an illusion. This spooky link is not just a theoretical curiosity. It is the foundational principle behind emerging technologies like quantum computing and quantum cryptography, promising a future of unbreakable codes and computers that can solve problems impossible for any machine today. Yet for all its mystery, entanglement does not explain the solidity of the objects around us. For that, we need a cosmic rule of personal space. The Pauli exclusion principle is a fundamental law of quantum mechanics that states no two identical fermions, a category that includes electrons, protons, and neutrons, can occupy the same quantum state at the same time. Think of it as the universe's ultimate occupancy limit. This is why electrons in an atom must stack into different energy levels, or shells, instead of all collapsing into the lowest, most comfortable orbit. This simple, unwavering rule is the reason atoms have structure and volume. It is the force that prevents you from falling through your chair, because the electrons in your atoms are repelled by the electrons in the chair's atoms, enforcing a strict boundary. Without this principle, all matter would collapse into a dense, featureless lump, and the complex chemistry of life would be impossible. This structural integrity, born from a quantum rule, finds its ultimate expression in the hearts of stars. Nuclear fusion is the cosmic engine that powers the stars, a process of immense power and beauty. In the extreme pressure and temperature of a stellar core, hydrogen nuclei are forced so close together that they overcome their mutual electromagnetic repulsion and fuse, creating helium and releasing a tiny amount of energy according to Einstein's famous equation. In the vast interior of a star, this reaction occurs countless trillions of times every second, the collective energy building into an outpouring of light and heat that can sustain a star for billions of years. This is the alchemy that forged the first elements after the Big Bang, and it continues to create all the heavier elements that will one day form planets and life. We are all, at our most fundamental level, the products of this stellar fire, a testament to a force that transforms simple atoms into the building blocks of the cosmos. That stellar fire forges the elements, but the stage upon which this cosmic drama plays out is still expanding, driven by a mysterious energy woven into the fabric of nothingness itself. The cosmological constant is Einstein's term, repurposed for the energy density of empty space. It is the mathematical representation of the vacuum energy we encountered earlier, a constant, relentless pressure inherent to the vacuum that pushes the universe apart. This is not an explosion from a single point, but the very space between galaxies stretching, carrying them apart like raisins in an expanding loaf of bread. The most stunning evidence for this comes from maps of the cosmic microwave background, the afterglow of the Big Bang. These maps reveal a universe that is geometrically flat and accelerating, a cosmic fingerprint that points directly to this constant, dark energy dominating the cosmos's fate. Etched into that same ancient afterglow is a subtler pattern, a cosmic ruler imprinted on the sky. Baryon acoustic oscillations are the frozen fossils of sound waves from the universe's first 400,000 years. In that primordial soup, gravity tried to pull matter together into clumps, while the intense radiation pressure of the young universe pushed it apart. This created a tug-of-war, setting up rhythmic, spherical sound waves that rippled outward through the plasma. When the universe cooled enough for atoms to form, suddenly becoming transparent, those waves were frozen in place, their final crests etched as a subtle, preferred distance between matter. Today, by mapping the positions of millions of galaxies, we can see this same scale, this echo of ancient sound, imprinted on the large-scale structure of the universe. It serves as a standard ruler, allowing us to measure the expansion history of the cosmos with incredible precision. Yet, even as the universe expands on the grandest scales, our local galactic neighborhood is caught in a powerful, specific current. For decades, astronomers noticed our Milky Way galaxy, along with our entire local group, is moving far too quickly against the general expansion of the universe. This motion points toward a colossal, unseen concentration of mass known as the Great Attractor. Located hundreds of millions of light-years away in the direction of the Centaurus constellation, this gravitational anomaly exerts a pull so immense that it is drawing our galaxy and thousands of others toward it. It is not a single object, but a vast, dense knot in the cosmic web, a supercluster of galaxies whose combined gravity creates a profound dip in the fabric of spacetime. We are like leaves on a river, floating on the cosmic expansion but simultaneously caught in a powerful local current, pulled toward a hidden destination we cannot yet fully see. This great attractor pulls us toward a specific point in our cosmic history, but to find the ultimate source of all power, we must journey back to the very beginning. The Big Bang was not an explosion in space, but the explosive birth of space and time themselves. From an initial state of infinite density and temperature known as a singularity, our entire universe, all of space, and time itself began to expand and cool. In that first searing moment, the four fundamental forces were unified as one. As the cosmos expanded and cooled, they froze out into the distinct powers we recognize today: gravity first, then the strong force, then the weak and electromagnetic forces. This event set the initial conditions for everything that has ever happened, from the formation of the first atoms to the evolution of life. It was the genesis of all structure, energy, and force. Yet our understanding of that moment hits a wall, a point where our current laws of physics simply fail. A singularity is a point of infinite density and zero volume, a place where the mathematics of general relativity break down. We encounter them in the centers of black holes and at the very start of the Big Bang. Here, concepts like space and time lose all meaning. It is not that matter is crushed into an unimaginably small space. It is that the very fabric of reality becomes undefined. This represents the absolute limit of our knowledge, a boundary beyond which we cannot see, hinting that a deeper, more complete theory of quantum gravity is needed to unravel the universe's final secrets. Could it be that our entire cosmic story is just one page in an infinite library? The multiverse hypothesis proposes exactly that, suggesting our universe is merely one bubble in a vast, perhaps infinite, cosmic foam. One leading theory, called eternal inflation, posits that the vacuum energy driving the Big Bang's inflation never truly turns off. Instead, in most of this inflating space, it continues forever, but in random pockets it decays, each one blossoming into its own separate universe with potentially different physical laws and constants. In this breathtaking view, the force of inflation becomes a perpetual universe generator, and what we call the Big Bang was simply the moment our local bubble formed. This leaves us with a profound question about the nature of reality itself. Are the fundamental forces we have counted constants of nature, or are they merely the local bylaws of our particular cosmic neighborhood, one chance outcome in an infinite ensemble of possibilities? From the ghostly pressure of vacuum energy to the absolute grip of a black hole, our journey has spanned the true titans of reality. We have witnessed the strong nuclear force binding the cores of atoms and felt the shockwaves of supernovas forging the elements of life. We have seen how the quiet rules of quantum exclusion give matter its solid form, and how the violent winds of entire galaxies can halt the birth of stars. These are not isolated phenomena, but an interconnected symphony of power, from the smallest quantum flutter to the grand expansion of all space. Each force, whether it builds or destroys, weaves a thread into the single tapestry of the cosmos we call home. We have mapped 30 of these fundamental engines, yet the universe is vast and its secrets run deep. This leaves us with one final, thrilling question. What incredible forces remain hidden, waiting just beyond the edge of our understanding, ready to rewrite the laws of physics once more? Let us know which of these cosmic powers you find the most awe-inspiring in the comments below, and subscribe to continue exploring the greatest mysteries of the universe together.